So, theorem. Weak Nullstellensatz. So, let K be any algebraically closed field then every maximal ideal in R, say R equal to the polynomial ring k x1 x2 xn is of the form for some A1 AN. As a consequence, a family of polynomials, this is important, we will see later, family of polynomials in K x1 x2 xn with no common 0 generates the unit ideal. So, this is a converse question which I asked. If they do not have common 0, that means it should be a union of, that means V of f is empty. So, then it should be a unit ideal. So, proof. So, first of all, x1 minus a1 up to xn minus an, this is always a maximal ideal, there is no doubt about it, right. You do not have any ideal containing x1 minus a1, x2 minus a2, etc. So, this part is obvious, x1 minus a1 you do it for one variable and then you use the induction. So, that you can see that is always a maximal ideal. So, question is converse, that every maximal ideal whether it is of this form. So, that is one needs to show. So, converse part. So, let M is an ideal, maximal be a maximal ideal. What we have to show, that if we show that M contains an element of a ideal of this form x1 minus a1 up to xn minus an ideal generated by this, then we are through. So, that should be the idea, that how to prove that these are the. So, every maximal ideal, any maximal ideal, then it should contain ideal of this form, then we are done, right. So, what you do? So, you take the ring R, which is the polynomial ring in n variable, take R to R mod M, right. Now, K, now this will contain the field K, right. So, now this R mod M, if I call it L, so R is a finitely generated K algebra. So, quotient is also finitely generated K algebra. Now, you use the so L is algebraic over K, L is also finitely generated over K. So, any finitely generated, if So, this is where integral extension comes here. So, if I take some L which is a finite type, that means finitely generated algebra over K, and then K, this L is algebraic over K. So, this will imply L is algebraic over K, because after all it is a finite type. So, if it is not algebraic, there will be some transcendental element. A transcendental element that won't be a finite type. If you take the, it will go on, because it is a finite type algebra. So, L is algebraic over K, but the point is the K is algebraically closed. Yes. Okay, so this is I'll just put a lemma here. Suppose K is inside R. R is a finitely generated K algebra. Then if R is a field, then R is algebraic over K. Because you see that if it is not algebraic, then it will fail, there will be some transcendental element, and that transcendental element will tell you that it won't be finite type. That is the rough idea. I mean, you have to prove it, you can take it as an exercise. So, here you will see some integral extension. If you can use, using integral extension also you can prove this kind of statements. Yeah. So the point is that this is why algebraically closed field is here. L is algebraic over K. K is algebraic, so L has to be K. Right. So, once it is over K, now you have this. So let us draw the diagram here again. So, you have this R to R mod M, which is K. Now, you have these elements xi's. Right. So, xi's, so this is xi's will go to some element ai, right. Now, you consider the ideal x1 minus a1, the ideal generated by this x1 minus a1, xn minus an. Now, x1 minus a1 will go to 0, because a1 will go to a1, right. This is a K algebra map. So, it will take K to K. So, this is a1, so x1 minus a1 will go to 0. So, this will be inside in some maximal ideal. So, ideal, say x1 minus a1 is going to 0, x2 minus a2 is going to 0, xn minus an is going to 0. So, whole ideal is going to, so this will go to 0. So, it will be inside M. So, this will imply that, because this is already a maximal ideal. So, this implies that M will be some x1 minus. Huh? Yeah, because it is a homomorphism, the natural map. So, xi will go to some element in R mod M, but R mod M is nothing but K, because K is algebraically closed field. So, it will go to ai for some ai. So, now you consider x1 minus the ideal generated by x1 minus a1, x2 minus a2 up to xn minus an, to contain in the maximal ideal. But this is already a maximal ideal. Yeah. But this is already a maximal ideal. So, M has to be, is a proper ideal, right. Okay. So, now how this helps you to prove the one which I was saying, that that if Vi is empty, then I is unit ideal, right. So, suppose, so as a corollary or consequence, see, so suppose, or consequence, the second part, so suppose F alpha, alpha belongs to lambda, be a family of polynomials with no common zeros. So, consider the ideal generated by this this set F alpha. If this is a proper ideal, if this is not an unit ideal, then it will be inside some maximal ideal which is of the form x1 minus a1, xn minus an. Because by previous we saw that they are the only maximal ideal. Now, if I take V both side, then this is the 0, this will be V of I, but V of this is nothing but a point a1, a2, an. So, that will say that a1, a2, an is a solution, it is inside the, but that is a contradiction, right. So, it has to be a, is it clear? Shall I write or not? Clear, right? So, this will say that this will belongs to V of I, but which is a contradiction. Because I started with I which has a which has no zero common zero set of. Okay. So, this is weak Nullstellensatz. So, now let us prove the strong Nullstellensatz. We will use weak Nullstellensatz in the proof. So, now here this is theorem, let us write theorem 1. Yes, theorem 2, strong Nullstellensatz. So, the statement is that, suppose again we will assume algebraically closed field. So, because we have to use this weak form, suppose k equal to k bar, let we are writing capital K, okay. Let's write capital. K is algebraically closed, let G and F1, F2, Fn or Fm are elements of K, x1, x2, xn. If G vanishes on 0 set of F1, F2, Fn, the system of equation, then some power of G lies in the ideal generated by okay. That means G is in the radical ideal of the F1, F2, F2, right. So, proof, consider. So, you have this kx1, x2, xn, you embed it into one, you increase the one variable. we embed it into K x1, x2, xn, the natural inclusion. So what I am going to use, it's called Rabin-Toish trick. So this was invented by, I think, Rabin-Toish. There are many proof of strong Hilbert-Nullstellensatz, but the proof which I am using is Rabin-Toish trick, and this is the best proof, I mean the simplest proof so far available. There are many people try to give different proof for this theorem, because it is one of the fundamental theorem in, it's like in analysis you have some theorem, right, like Bolzano-Weierstrass theorem or some basic theorems which are used daily. So this is kind of a daily theorem for the first theorem which is in algebraic geometry. Okay. So this is called Rabin-Toish trick. So I am going to use that. That same proof. So consider polynomials and polynomials. F1, Fm, xn plus 1, g minus 1. Right. So now you see that g vanishes on f1, f2, fn, right. So then and g is a polynomial in x1, x2, xn, right. So this set, this has no common solution. Because if it has a common solution, then f1, because g vanishes on x1, x2, xn, on the 0 set of f1, f2, fm, so then it will be minus 1, right. So this polynomial, so it has no common solution. So now you use weak Nullstellensatz by weak Nullstellensatz. It generates the unit ideal. Unit ideal in k x1, x2, xn plus 1, because there is in k x1, x2. Right. So that means you can write 1 as some p1 f1 dot p m fm plus p m plus 1 x m plus 1 g minus 1, right. Now you consider this homomorphism phi from k x1, x2, xn plus 1 to k round bracket x1, x2, xn. So k round bracket x1, x2, xn is the quotient field of the polynomial ring k x1, x2. So you send xi goes to xi for I equal to 1 to n, and xn plus 1 you send it to 1 by g. Right. So now it is this is a k algebra map. So 1 will go to 1 here. So if I apply phi, so what will you get? You will get 1 equal to p1 of x1, x2, xn plus 1, xn 1 by g f1 plus p n plus p m x1, x2, xn 1 by g and xm plus 1 is going to 1 by g. So, this part will go to 0, right. So, this will be equal to 1, but these are polynomials. So, if you clear denominator, then what will you get? Some g power something will be in the ideal generated by f1, f2, f2, k of k x1, x2, x2. So, you are done. I is the ideal generated by f1. So, this is I will write down the name of this person because it is a very nice proof of Hilbert-Nullstellensatz, which is a very basic theorem. It is not very easy. I mean, there are many proofs in many books they have given, but this is probably the easiest proof of. This method is called Rabin. It's known as Rabin-Toish trick. Even it is so famous that it has a sorry. It is so famous that it has a Wikipedia column in the web. This trick. It is used in many things in many proofs in algebraic geometry. This clearing denominator we will see again in many places. But okay, so we will stop here.